Let's talk about the Runge-Kutta method. There are three ways to solve differential equations. You can do it analytically by finding a function that fits the differential equation. You can do it graphically using slope fields. Or you can do it numerically. You can estimate the numerical solution using a method like Euler's method. Runge-Kutta fits into this last category. Runge-Kutta methods are like Euler's method. The calculations are more complicated, but the results are more accurate than those we get from Euler's method. Runge-Kutta method was developed by Carl Runge and Martin Kutta, two German mathematicians, in 1901. Here's an example. Suppose y prime equals 2xy, y of 1 equals 1. Use a fourth order Runge-Kutta method, RK4, with step size h equals 0.1 to obtain a 4-decimal approximation to y of 1.5. Here's the general idea behind Runge-Kutta. Suppose we're given an initial value problem, dy dx equals f of xy, y of a equals y of 0, and we want to estimate y of b. So in other words, here's a, we know y of a, and we want to estimate y of b. We can estimate y of b and y of x for values of x between a and b in the following way. Choose a step size h. Subdivide the interval from a to b into subintervals of length h. Here's what we do with it. Starting with h0, find these. k1 equals f of x sub n y sub n. k2 equals f of x sub n plus 1/2 h, y sub n plus 1/2 hk1, etc. And use them to calculate y sub n plus 1, which is y sub n plus h over 6, k1 plus 2k2 plus 2k3 plus k4. Repeat the process until x sub n equals b, and then y sub n will be your estimate for y of b. If it looks complicated, that's because it is. So again, returning to the problem we looked at a moment ago, we're going to solve this using RK4. So y prime is 2xy, y of 1 equals 1, that's our initial condition. X is 0, y is 0, that's our initial value, that's 1, 1. And h equals 0.1, that's our step size. We saw a moment ago that k equals f of x sub n, y sub n. This again is our f of xy. So k1 I should say, is f of x sub 0, y sub 0, because again we're starting off with n equals 0. That's going to be f of 1, 1. In other words, it's going to be 2 times 1 times 1, which is 2. Okay, that's k1. k2 is f of x sub n plus 1/2 h, y sub n plus 1/2 hk1. In other words, it's going to be 1/2 of, this is x0, x sub n, plus 1/2 h, h in this case is 0.1, that's our step size, y sub 0, that's 1, plus 1/2 h k1. k1 we already found a moment ago was 2, so we're going to plug that in. Okay, so that's our k2. This simplifies to f of 1.05, 1.1. In other words, 2 times 1.05 times 1.1, or 2.31. k3 is f of x sub n plus 1/2 h, y sub n plus 1/2 hk2. In other words, it's f of x0 plus 1/2 times 0.1, that's our h. Y sub 0, that's 1, plus 1/2 h, that's 0.1, times k2. That was 2.31. We just found that a moment ago. In other words, it's f of 1.05, 1.1155, which turns out to be 2.34255. Again, we're just evaluating 2xy, twice x, y. k4 is f of x sub n plus h, y sub n plus hk3. So in other words, it's going to be x0, which is 1, plus h, which is 0.1, y sub 0, which is 1, plus h, 0.1, times k3. We found that a moment ago. That's k3. That is, in other words, f of 1.1, 1.234255. And because f of xy is 2xy, this turns out to be 2.715361. And then we put all the pieces together. So y1, oh man, this is brutal, isn't it? Okay, y1 turns out to be this. It's going to be, we saw this a moment ago, if you want to look back at what that's going to be. Okay, y1 is y sub n plus h over 6 times k1, 2k2 plus 2k3 plus k4. So applying that here, We end up with y1 equals x sub 0, that's 1, plus h, which is 0.1 over 6, times y sub n. That's k1, that's 2, plus twice k2, plus twice k3, plus k4. And that all adds up to 1.2336745. That's y1, that's our estimate of f of 1.1. And then we just repeat the process. Okay, this is 1.1. So now we figure out k1, k2, k3, and k4, and use those to find y2. So k1 is going to be f of, these are brutal, isn't it? It's f of x1, y1. In other words, it's f of 1.1, 1.2336745. So it's twice 1.1 times 1.2367435, which is 2.7140837. K2, this is going to be our expression for K2. That simplifies to f of 1.5, 1.36937858. In other words, it's twice x times y, which is 3.149570616. K3, again, you know the formula for K3, you've got that. That's what we end up with. Turns out to be f of 1.5, 1.39115281, which is 3.199651626. K4, this is our formula for K4 from before, which is f of 1.2, f of 1.2, 1.553695513, which turns out to be 3.728734883. And so y2 is just going to be y sub 1 plus 0.1 over 6, in other words, h1 over 6, k1 plus 2k2 plus 2k3 plus k4. That turns out to be 1.552695398. So that's roughly f of 1.2. Okay, so this is what we get for x2, y2. 1.2, 1.552695398. So we would just repeat the process in the same way. We'd use x2, y2 to find x3, y3. We'd use that to find x4, y4, and then we'd use that to find x5, y5. So notice, we're done. So this is x sub 5, that's 1.5. That's what we wanted to estimate. We wanted y of 1.5. So this, my friends, is an estimate of y of 1.5. You have got to check your answers when you do this. What you don't want to do is calculate at y sub 5 only to find out that it's wrong, that you made a mistake. That would be brutal. So what I'd suggest you do is go to some slope field and direction field plotter. I like this one from Bluffton University. There are lots of them online. Here's how the way the front one from Bluffton works. So enter dy dx, that's 2xy. In this case, you choose RK4 with step size 0.1. And then you click on initial points. Your initial point is 1, 1. You click submit. And you end up with something that looks like this. That's cool. So that's the graphical solution. And then you click on table. And here's what it gives you. It gives you this table. So notice we get these numbers. And what we ended up with was 3.49021. So again, what you want to do is once you calculate f of 1.1, once you get your estimate of y1, just make sure that your estimate is the same that you get from this slope field plotter. Because if it's wrong, go back and check your work.